Hey, good morning, everyone. It's time to get started. Today we have a guest lecture. Our grad student Vignesh here is going to tell us tell us about system Verilog, and it's going to be a fairly dense lecture. He's going to be able to, he's going to cover a lot in the next 80 minutes. So pay attention. Vignesh, take it away.
All right, thank you, Bora. Can you hear me fine and see my slides?
Yes.
Yes, perfect. Okay. So actually, I can't see any of the chat. So Bora, if you see anything in chat, just unmute yourself and tell me the question. And everyone's free to ask questions at any time. Okay, so yes, as Bora said, I'm going to talk about System Verilog for design and verification. This is a pretty dense lecture, so I'm hoping that we can go through it in the next 80 minutes. And let's get started. So what is the intention of this lecture? As Hassan and Sophia may have told you already, we use Chisel for all the RTL that's written in Berkeley, things like Gemini, Rocket Ship, all the stuff in Shipyard. So if we're using Chisel to write all this RTL, why bother learning or even looking at System Verilog? And the simple reason is that System Verilog is the de facto industry standard for writing RTL and for verifying it. System Verilog and the library used for verification, known as the Universal Verification Methodology, or UVM, is used in nearly all industry verification. So you will almost certainly be asked something about it in your interviews. So it's useful to know some things about System Verilog. It's also useful to understand some basic dynamic verification concepts. So I'll go over things like test bench hierarchy, organization, how to generate stimulus, things that will come in handy even if you use Chisel to write your RTO and you use Scala to verify it. You also want to have the skill to understand existing System Verilog code. There's a lot of IP out there that's written in System Verilog. So you do want to understand why it's written a certain way. What does every net type mean? What are the constructs in System Verilog? And I think a very interesting point here is we also want you guys to get some exposure to System Verilog so that you can think about ways to improve Chisel. So there are ways that System Verilog is deficient, but there's also ways that Chisel is deficient. And hopefully after you see this presentation, there may be some inspiration you get as to how to make Chisel a better design language. So let's go to the next slide about what is System Verilog. So System Verilog is an IEEE standard. So it is well defined in a thousands of page specification. It is a massive extension of Verilog that has brand new constructs for design and verification. So it's a superset of Verilog. You can use all the Verilog constructs in System Verilog code, but there's a bunch of stuff added on top. And the stuff includes new data types that are used for writing RTL and new data types that are used for test benches. There is support for object-oriented programming, which we'll get to. There's a constrained random API that allows you to generate random stimulus that is constrained using arbitrary Boolean formulas. There is a specification language called System Verilog assertions. And this is very useful for writing temporal properties. And we'll talk about this in more detail as well. And there's a coverage specification API. So a way to specify what type of things you want your simulator to track as you're simulating your RTL. So you know whether your test has accurately covered all of the RTL that you wish to cover. And we'll get to that in detail as well. The other thing that System Verilog does is it tries to fix a lot of warts in Verilog. And a lot of these pertain to synthesis and simulation mismatch, where you take your circuit in RTL simulation, you get one behavior, and then you take your circuit post-synthesis simulation and you get a different behavior. This is obviously not desirable, so there's a few constructs added in System Verilog to prevent this. And the reason is Verilog was initially developed as a simulation language. So the use of taking, so the synthesis tools that took the simulation constructs and turned it into synthesizable hardware came much later. And so System Verilog introduced a few things to try to resolve some problems here. So in this first part of the talk, I'm going to talk about System Verilog for design. Everything in this section is synthesizable, meaning it's stuff that you include in your RTL and things that the synthesis tool understands how to convert into hardware. in the latter part of this talk, I will get into system Verilog for verification, which covers constructs that are not synthesizable, that can only be simulated. So the first really neat thing in system Verilog is you get to end this confusion of when to use wire and reg. So you may remember in Verilog 2005, we use wire for the left-hand side of assigned statements, and we use reg for the left-hand side of any code that is inside an always at block. Now, so here's an example. You have a wire A and registers B and C, or reg type nets B and C. And this means A can be assigned using an assign statement, and B and C must be assigned inside an always at block. And it can be always at star or always at any arbitrary event, right? And you can put whatever you want on the right-hand side. They can be other wires or other regs. But that's really annoying because if you want to move an assignment from an assign statement to an always block, now you have to change the type of the net to wire, from wire to reg. So in system Verilog, these two things are unified. So now in system Verilog, you use logic for the left-hand side of assigned statements, and logic is also used for the left-hand side of code inside always at blocks. So now A, B, and C can all be declared with one net type called logic. And logic allows you to assign A, B, and C in an assign statement or in an always block. You don't have to think about it. In both of these examples, however, what determines whether the net is the output of a register or combinational logic is the containing statement, right? So if the containing statement for an assignment is an assign statement or always at star, that means the left-hand side refers to the output of combinational logic. Whereas if the containing block is always at an event, an edge triggered event, like this pause edge clock, then whatever is assigned inside there, like C, refers to the output of a register. So that still remains. The location where you perform the assignment determines what that net actually represents in hardware. But now you have just a single net type used to describe all three. Okay. The other neat thing in system Verilog is you have a way to signal the intent of what you want to infer with these specific always blocks. So over here in the Verilog land, we have always at star block, and something that is on the left-hand side of always at star is going to infer as combinational logic, as we talked about before. And if we have always at pause edge clock block, then anything on the left-hand side, like C here, is going to be inferred as the output of a register. And in Verilog, this coding style is used to verify that C infers as a register and B is combinational logic. So you have to follow this exact coding style here to make sure that you get the hardware that you intend. In system Verilog, there's two additional constructs that we introduced that make this a little bit safer. So if you want to do combinational assignments using an always block, there's this always underscore comb statement. And this makes sure that everything inside here will always infer as combinational logic. If you do something in here that is illegal, then the synthesis tool will warn you about it. It will also enforce that you use blocking assignments inside of the always comp block. And similarly, there's also an always FF block. And this will always infer a flip-flop as the left-hand side of any assignments made inside of it. So all these statements do is they let you signal your intent that this block is inferring registers and this block is inferring combinational logic. Okay, the other neat feature is these implicit port connections. So how many times have you done this in your 151 project? You declare a module and you want to hook up the inputs of a module when you instantiate it, right? So in the top level where you instantiate this module, you have to declare a bunch of wires, then route the wires to this module. Then you may want to route those same wires to a different module. And every time you have to specify, I want A connected to A, B connected to B, and C connected to C. But that is such a common pattern that there is now a shortcut for it. So if the net names and the corresponding port names match, like they did on the example above, where you instantiate mod, now you can just use this dots notation. So I want to connect A to A, B to B, and C to C. But in system Verilog, there's even more concise shortcuts. This is the wildcard implicit port connection. You can just do dot star, and this will connect every A, B, and C in the top level where you instantiate the module to all the module's ports. So important note here is these implicit connections only work if the port names and widths match. So they need to match exactly. You have the option to override certain ports by manually specifying them with this dot star notation, but otherwise everything needs to match up exactly. And so this prevents you from making unintentional bugs. But keep in mind that this is kind of a feature of System Verilog that is quite controversial. There are some people who don't want to see this in their code, and there are some coding guidelines at companies that prevent this, the use of implicit port connections. But you probably want to use it in your RTL because it's fun. Okay, the next interesting thing in System Verilog are the support for enums. Enums now are a first class type in System Verilog. So you may remember in Verilog, in order to declare constants and to bind those constants to hardware values, you use local params. So when you're creating an FSM, you might declare a local param for each state that you may want to have in some state register, right? And then you match on the current state that you're in, and then you assign the next state. So you use these names in your local param to refer to these states. In System Verilog, we have a much saner way of doing this. You can use an enum, and an enum is just nothing more than enumeration. You have a way of specifying distinct values that a particular enum variable can take on. So in this case, state T can have 3 values: state idle, state A, and state B. And the type of this state T net is a logic 1-0. So this is a 2-bit hardware signal. And then instead of declaring a register using this reg10 syntax, you actually can use state T as a net type. So state now is of type state T. State T, of course, is just a alias for enum logic 1-0. And now you can use the enum in the same way you've used the local param in the always block. So these enum names are available for you in the global scope in a given module, and you can just assign them like this. You can use their values, and you can assign particular enum values to state. So nice thing about enums is that they automatically check whether all these values can fit. So if you declare a 2-bit enum, then it makes sure that you have no more than 4 values that can go in there. They can be used as net types, as we just talked about. You can declare a state T state. And the important thing about enums is that they add the semantic meaning to constants. So enums are used all over the place in System Verilog because they help you make it very clear what your intent is with a given signal. And I'll talk about that in the next slide here. So enums are, as I said, used for attaching semantic strings to values. So instead of having a 1-bit input to a memory that indicates whether you want to read or write to that memory, you may instead want to define an enum that defines a memory operation. So now in your memory module, you maybe specify that I take some address, I take the data in, and I output some data out. But now instead of using a 1-bit signal here to indicate the operation you want to perform, either read or write, you now take in a mem op t. And this gives, this is much easier to read because now the meaning of read and write are completely well-defined. You don't need to look in a table or documentation to realize whether read is equal to 0 or equal to 1 for this op signal. The other interesting thing to note here is that these input and output data types, these input and output net types that we talked about in Verilog before, remember that by default, they are all wires and you can override them. So in the same way that in Verilog, you may have written output reg whenever you wanted to assign an output inside an always block. Now you can just override an output as logic, and it will enable you to write d out inside an always block or in an assigned statement. So this is very common practice in System Verilog RTL. Okay, and even more on enums. Enums are quite powerful. So you can force enum values to be associated with a specific value. And this is very useful when you want to take an interface that doesn't use enums and you want to use enums to connect to them. So in the previous example, let's say you had a memory that took a single bit input to determine whether you wanted to perform a read or write, and it wasn't an enum, but you wanted to construct an enum so that you can safely assign this value. You can encode the information about what is a read and what's a write. So you can do that using this construct here. This part is the same, but now every value of the enum can be assigned to a particular hard value that you wanted to take on. So now if you refer to state idle in your code, you actually refer to the constant 3. The other interesting thing you can do is generate n enum values without typing them out. You can use this syntax here. You just take any value name, any literal constant, and you in brackets put the number of enum values you want to generate out. So you put 3, then it automatically generates these names for enums behind the scenes and binds them to the values 0, 1, and 2. So now in your RTL, you can use state 0 to refer to the zeroed state, state 1 to refer to the first, and so forth. And also you can generate n enum values in a particular range. So if you want your states to start at numbering from 3 and going to 5, for example, then you use this construct and you generate state 3, state 4, and state 5, and they are bound to 0, 1, and 2. So these are just shortcuts you can use. There's actually a ton of these shortcuts defined in System Verilog. Enums are a first-class data type in System Verilog. And so what this means is that enum instances, like that state t state that we defined before, they have functions that are defined on them natively. The functions include things like next to get the next value of the enum, previous to get the previous value, num for the total number of elements in the enum, and name, which returns a string with that enum instance's name, the current value that it's on. And this is very useful for printing out an enum using display. Enums are not perfect though. They have one big flaw, is that they are weakly type checked. Many tools prevent you from assigning a binary literal to an enum type net if they're in the strictest warning mode. But as I mentioned, this is a weak type check because this is still allowed by the System Verilog language. It just may be disallowed by some specific tool settings. The other interesting thing about enums is that they show up in waveforms. So this is really useful because you guys may have been writing some RTL and you define these local params for your FSM that map FSM states to a given literal. And now when you look at your waveform, all you see is in your state register, you just see the literal that the state represents, right? 1, 2, 3, or 4, something like that. If you use enums, then the name of the enum will actually show up in the waveform. So instead of seeing 1, 2, 3, 4, you actually see state idle, state A, state B, state C. So there's no more confusion trying to correlate literals to a semantic name, and that's very convenient. Another interesting feature, stepping away from enums in System Verilog, is a multi-dimensional packed arrays. So in Verilog, you are only allowed one packed dimension in your array, and I'll explain what that means. So packed dimensions are specified to the left of the variable name. So take this declaration, for example, logic 70A. Packed dimensions are contiguous. So what this means is that A refers to a net that has 8 bits that are all contiguous, all put together. On the other hand, you have unpacked dimensions that are written to the right of a variable name. And these unpacked dimensions are non-contiguous. So here's an example. You have logic A8, and this means that you have 8 different 1-bit values that are specified by this net A. So how is this actually used? So you may have seen stuff like this when you try to declare a behavioral model for a memory or a synthesizable model in the case of an FPGA. You may have something like logic 31.0, memory 32. What does this mean? It means that this is the packed dimension. So you have rows of 32 bits, And then on the right here, you have the unpacked dimension, which means you have 32 such entries. So memory denotes a 32 by 32 memory. If you index the first dimension of memory, you're indexing on the unpacked dimension. The first unpacked dimension, and all the unpacked dimensions are 32 bits wide. They refer to the packed dimension. The issue here is you cannot represent more than one dimension in memory 0. So you cannot add additional packed dimensions over here in traditional Verilog. And what this means is you can't easily byte address the memory. So let's say you wanted to index this memory by not only looking at a particular row of the memory, but you want to look at a particular byte in a particular row. You can't do that easily in Verilog. But now with System Verilog, you can add multiple packed dimensions. And now what this says is I still have a memory that contains 32 rows, but now each row is made up of 4 elements that are 8 bits wide. So you have 4 bytes that make up each row. And now this allows you to not only index memory 0 and get back a 32-bit wide value, but now you can index memory 0 and take the 0th byte of the first row of memory. And that gives you 8 bits. And you can take the second byte, and that gives you another 8 bits. So now you have the ability to index the memory byte-wise as well. This is very useful when you write RTL that needs to index multidimensional nets in very precise manner when you want to pack multidimensional data. This may be useful in things like ROBs or caches. Okay. The next interesting feature is structs. So structs are very similar to bundles in Chisel. They allow you to group nets together, and they help you encapsulate groups of signals that need to be carried together throughout your design. And they give you a very easy syntax for declaring this entire group of signals as one group. You don't need to declare each of the signals inside a struct individually if you want to use them in your module. A struct can be used within a module or in a module's ports, and structs themselves cannot be parameterized. This is in contrast to modules, and later we'll talk about interfaces that can be parameterized, but structs can be created inside a parameterized module or interface. So let's look at this example here of a struct. There's this packed keyword when you declare a struct, and this means that all the elements of the struct are placed together in contiguous memory. This means that if you declare a net of this struct type, that you will get basically 32 plus 8 plus 4 plus 1 bit vector that this struct represents. So it's just a single vector that it boils down into when you synthesize it. A struct can contain logic elements, and they can be any dimension you want. They can also have unpacked dimensions as well. You can have a enum also inside a struct. You can pretty much put anything you want inside a struct. You can nest structs, so you can put another struct inside a struct. So this struct over here is intended to represent all the data that you need to give a command to a RAM, let's say. So if you want to tell a RAM to do something, you need to give it a data address, a write enable, and an operation. And so here, when you declare the RAM module, you can say that the RAM takes in this command as a single struct argument, a single struct port, and it puts out this dout. So this allows you to simplify the syntax when you want to reuse that command struct multiple times in your RTL. And then let's say you're looking at the place where you want to instantiate the RAM. And so if you want to basically have an instance of the struct that you use to for assigning values to that struct, and then you pass that struct into another module as a port, you can declare anywhere in your RTL a struct like this. So this gives you an instance of RAM command called A, and A contains all of the ports of the struct. So now you can do something like a.dn and give it a particular value, a.adder and give it a particular value, and so forth. That's actually a typo here. It should say a.dn. We're referring to each member of this struct A and assigning each one. So let's talk now about interfaces. So interface, like structs alive together nets, interfaces can be parameterized. And as I mentioned before, they can contain structs. But in addition to that, they can also contain initial blocks that have assertions about the port parameterization and whether a particular port parameterization is legal. And it can also include other verification collateral. And these are oftentimes system Verilog assertions, which we'll talk about later as well. And interfaces allow you to simplify connections between parent and child modules. So here's an example of an interface you might declare for RAM. So this is replacing the example in the previous slide. We want to just fully specify what the interface for this RAM module ought to look like. And as I mentioned before, an interface can depend on parameters. So you have two integer parameters here, adder bits and data bits, and they are reflected in the number of bits that are assigned for each of these ports, adder D in and D out, that are members of the interface. The interface depends on a clock, and it's pretty typical to put the clock as a not a member of the interface over here, but as an argument passed to the interface. We'll talk about why a little later. And finally, you have this memory operation as well. So now, if you want to construct this RAM module, instead of elaborating all the ports that you want inside this list, you just specify I want a RAM interface, referring to this interface type. And INTF is your binding for it. So now inside the RAM module, you can use INTF and refer to any of its members in order to assign them. So over here, at the posage of the interface's clock, I want to assign the interfaces D out with some RAM that I have inside of this module, and I want to use the address that I get from the interface. And if you want to instantiate an interface in order to connect it to a module that you instantiate, so here you have RAM R and it takes an interface. So how do I get an instance of this interface? It's very simple. You instantiate the interface itself, RAM IF. And then when you instantiate it, you specify its parameter binding, just as you would instantiate a module. And then you specify its particular name. And actually over here, you're also supposed to provide any arguments the interface expects, which in this case would be a clock, but I haven't written it down in this example. And now you can just assign every member of this interface. And when you bind the interface to the RAM R, all the assignments of this interface will be driven into this RAM. So this is very convenient for abstracting away common interfaces in your design. But a big problem here, I didn't actually specify the direction of the interface ports, right? I didn't specify what is an input and what is an output. And that's a problem because this can cause multi-driver issues if you have improper connections, and it can cause in-out port coercion. So what is the solution here is to use mod ports. So in the interface declaration, everything is the same. You still specify all of the logic signals that I had in the previous slide. But in addition to that, you can specify these mod ports. And mod ports are ways of specifying groups of signals in your interface that are to be used as inputs and outputs. So for the targets in reference to the RAM itself, the RAM has the address, data in, op, and clock as inputs, and the data out as an output. And in reference to the controller, whatever is controlling the RAM, it puts out adder, D in, and op, and it takes in D out and clock from the RAM. It takes D out from the RAM and clock from the top level. And so now when you declare the RAM, you not only declare the interface, but you also declare a mod port as part of that interface. The slave really should be targets. And then you assign the interface in a typical way. So now you've encoded that D out is indeed an output of this RAM, clock is an input, and adder is an input. Okay, throughout this entire presentation so far, you've probably seen typedef everywhere. Like I've used typedef for enums, I've used typedef for structs. So what does typedef do? It is used to expose these user-defined types with an alias. So just like enums, they help to attach semantic meaning to your design. You can use typedefs to alias any type. So they can be used to give a global name for an enum, a global name for a struct, and they can be used to give global names for particular data types that are too small to fit in a structured enum. They are just a single data type. So here we have the signed logic 70, and I want to alias that type as signed byte. So now anywhere in my code, I can use signed byte as a shorthand for signed logic 70. And same thing you can do with something like unsigned logic 30 and refer to it as cache index. So this is a really good way of attaching semantic meaning to your design. And I highly encourage you guys to use this in addition to structs and interfaces.
So Vignesh, can I ask a quick question?
Yes, yes.
Yeah, earlier in the mod type, in the interface, so when we declare interface, is that specific mod ports? Yeah, basically for this interface, is that like specific to a particular module, or we also need to differentiate like global interface versus local interface?
So the interface over here, this RAM-IF is global, and you can use it in as many modules as you want. So a common practice would be to declare an interface for like AXI4 or an interface for APB or interface for TIE-Link. And you could use that same interface definition in all the AXI bus components you have in your design.
I see. So let's say we want to manage a project with like a big module, a top level project with like multiple submodules. We should put our interface declaration in like one place that actually dictates how different modules interact with each other.
Exactly, yeah. So you would put all your interfaces in one package, and you would import that package in every module that you want to use the interface with. And I'll get to packages in that very next slide.
Okay, wonderful. Thank you.
Okay, yeah, that was great. So now, like, how do you actually organize all this code? It seems like I've just spat out a bunch of data structures that you could put anywhere, right? So System Verilog has a solution for that as well. And those are packages that provide namespacing. So you may be familiar in Verilog, you have a global namespace. All the module names that you declare can be referred to from any other module. You can have includes that have defines in them, but this is very hacky and requires all kinds of if-def guards to make sure they don't get included multiple places. Large projects have naming conflicts, so there may be one team that calls their FIFO FIFO and another team that calls their FIFO FIFO, but they have different implementations. And this is not going to work in Verilog because there's a global namespace. These two things will collide. So System Verilog allows you to encapsulate all these constructs I talked about in a package. So things like modules, functions, structs, type defs, classes, and interfaces can be put inside a package. And this restricts the scope of those constructs to that package. So here you have a package, my package, and it can contain anything. It can contain enum, like this state T declaration. It can contain a function, like this show vals function. So the show vals function is particular to the state T enum. So it creates an instance of this state T called S, starting with state 0, and then it iterates through all the different elements in state T, and it just displays their name and updates their value with s.next on every loop. So it's just a dumb example of a function that you can include in your package. But as Sophia mentioned, you can also include an interface in your package. And then you can import that package in your module declaration and reuse that interface. So here's an example of how you do it. You just do import my package, and then : refers to a package member. You can put star here, which imports everything in that package, or you can specify the exact names of things that you want to import. And then you can use those things inside your module. So in this case, our module example contains a state T enum declaration, which was defined in this package. Okay, so that's how to encapsulate things and make your code nice and clean. So that was a lot of stuff, but so far that is only System Verilog for design. Now I have 45 minutes to go over System Verilog for verification, which is much bigger than System Verilog for design. Keep in mind that everything in this section for verification, I'm going to be describing non-synthesizable constructs. So these are things that you wouldn't put inside your RTL. If you intend for them to be synthesized, they are purely for simulation and verification. So yeah, as I mentioned, it's massive. Yeah, go ahead.
Can I?
Yes.
Yeah, sorry. For the synthesis part, just from the tooling point of view, when people actually like for the EDA vendors, when they actually start like building tools to synthesize system Verilog, would that be basically they can leverage the existing Verilog synthesis flow, but supporting those features, or what they actually had a completely different flow just to get system Verilog synthesized?
I have a feeling that most people have completely rewritten their parsers and stuff like that to understand the system Verilog constructs natively. It's a massive undertaking to implement a system Verilog parser, even for just the design subset of the language. So that's a good point you brought up, is like, what is the vendor support for all this stuff? So everything that I talked about so far is well supported for commercial synthesis tools. So things like Genus and things like Vivado, they support pretty much everything I've talked about out of the box, no major issues. However, for verification, their verification is much more difficult to support every single construct. So there's a lot of missing holes in system Verilog for verification that are not all implemented in all tools.
Interesting, thank you.
Yeah, so I'm going to go over a few things from the system Verilog verification spec. It's going to be these 5 things over here. So I'm going to talk about these new data structures that we use for writing test benches. And this basically gives you parity with PHP type of data structures. So I'll talk about that a little bit later. You have object-oriented programming structures. Again, these are not synthesizable. They're only for test benches. You have system Verilog assertions, which is a specification language I'll talk about. There's a coverage API, and there's a constrained random stimulus generation API. All of these are part of the official system Verilog spec. So this is a little interesting because some of these may be considered like libraries that you could add to system Verilog, but they're actually baked in as part of the spec. They are part of the system Verilog standard library. So all simulators have to support them. Few data types. There are a few new, very simple data types. There's a bit, which represents a bit vector. It can be created just like logic. You can do bit 70 something, and that gives you a 8-bit bit vector. There's short int, and long int. These refer to 16-bit, 32-bit, and 64-bit integers. The reason why there's a bit type that is different from logic is that bit is a 2-state type. And in fact, all of these are 2-state types. And what that means is bit can only contain a 1 or a 0 in each bit position. In contrast, a logic can contain a 1 or a 0. It can also contain an X or a Z. And those are known as 4-state types. So 4-state types are used in your RTL, where you actually want things like X propagation to occur, where you may want to see Z's in your code that indicate something has been improperly connected. Whereas in your test benches, you want to use these 2-state types because you care more about performance and you don't want to bother simulating X's because those don't actually exist in your test bench. They don't represent anything real. There's also a native string type now. So instead, in Verilog, you had to declare an ASCII array, like an array of ASCII characters in order to have a string-like construct. But now string is a natively supported data type. And there are some helper methods that are defined on string, something that you might see in the C standard library, things like substring and length of a string and things like that, and tokenization as well. So there are these easy data types, and now there's some more interesting data types. So dynamic arrays. So typically in Verilog, all the arrays are fixed length at compile time. So here is a 3-element array of 4-bit values called R, and you can assign R using an array literal. The way you do that is you have an apostrophe, and in brackets, you can put the values you want the array to take on. But now System Verilog adds support for dynamic arrays that are sized at runtime. And these are very useful for generating variable length stimulus as an example. So here you might have the same thing. You have an array that contains 4-bit values, but its size is not specified at compile time. And instead at runtime, you can instantiate this array with a particular fixed size that is determined at runtime. So this doesn't need to be hard-coded too. This too can come from parsing an input. It can come from any source you want. And now you can use the same literal assignment syntax if you would like. You can also reassign this array handle to point to a different array of size 10. And you can index each of the individual elements like this. So array 3 equals 4 as an example. So that's pretty simple, but usually what you don't want is a dynamic array. What you actually want in many cases is a queue. And queues are very similar to lists in both Scala and Python. They are dynamically expanding data structures that keep track of a sequential list of values. And queues are very useful for hardware modeling. So if you want to model things like a FIFO or a stack, and anytime you want to process something sequentially, it's very useful to use a queue. So how do you declare a queue? You use this syntax over here. So you have here a queue of 4-bit elements. And to declare a queue in brackets, you put a $sign. I don't know why $sign, but that's what they went with. So you can also initialize the queue with a starting set of values. So here you say that the first 4 values of the queue are 1, 2, 3, 4, but the queue can be expanded after that point. You can fetch elements from the queue using simple indexing. So the first element, if you want to fetch the last element, use the $sign. You can insert new values into the queue using the .insert function. You can fetch a subslice of the queue. This is just like taking a slice of a list in Python. So here you take a slice of the queue where you exclude the first element, 1 to $. You can pop and push things to the front of the queue. You can also pop and push things to the back of the queue. And popping will take an element and return it to you. So now this X can be used somewhere else in your code to model hardware. And then you can clear the queue. There's this weird syntax that is used for taking this existing queue and turning it into something that has no values. There's actually no like .empty function that's defined on the queue. So now you have something similar to Python lists. That's very convenient, and that didn't exist in Verilog. And now you also have something similar to Python dicts or Scala maps. You can declare this associative array in System Verilog. So here you have a dictionary called fruits, and the key is of type string, and the value is of type int. You can use this literal assignment syntax with this apostrophe to say I want apple as the key, value 4, orange key, 10 is the value. You can, of course, index into this associative array with any key you want. You can check if a particular key exists, like lemon, which in this case does not, and you can delete a key that exists. So I'd say this is on par with the functionality that you get from a language like PHP, and similar to the functionality you get from Python, albeit with a much weaker standard library than Python. Okay, one very useful feature in System Verilog for verification are these clocking blocks. Oftentimes when we write test benches, there is a lot of confusion as to when we have to drive the DUT inputs and sample the DUT outputs relative to the clock edge. So many times we'll do things like, if something doesn't seem to work in simulation, then we might just put like a #1 after we drive an input, or we might want to put a #1 after we do a positive edge of the clock in order to sample the outputs from the DUTs. So this is very hacky behavior, and the people who wrote a lot of Verilog understood that this needs to be encoded somehow in the language specification itself. And so now there's a solution in System Verilog. We want to encode this behavior of when we drive the DUT inputs and sample the DUT outputs in an interface by using these new constructs called clocking blocks. And so here's the interface we had earlier. The RAM interface has these members as part of the interface. And now you can also define this new construct called a clocking block. You give a clocking block a name called whatever you want. You specify the event on which the clocking block should happen. So the pause edge of this clock that we refer to here. And inside the clocking block, you use this arcane syntax to tell the tool what exactly, how you want to drive the inputs and how you want to sample the outputs. So let's use this graph here to clarify things. So the clocking block allows you to specify relative to an edge of the clock, in this case, this rising edge. It allows you to specify how far before the edge you should sample the outputs of a circuit and how far after the edge you should drive the inputs for a given circuit. These are called input skew and output skew. And you define them in this statement over here. So over here, what we're saying is for every input, I want to set the input skew to #1 step. What this means is I want to sample the inputs right before the rising edge of the clock. This one step is used to tell the simulator, I want to sample it right before the rising edge. Again, this syntax is a little weird. And of course, you can also specify the output skew. So the output skew here is specified as neg edge. What that means is we drive the outputs at the negative edge of the clock. What's useful is that these skews here, 1 step and neg edge, they can be replaced with any delay value or any edge event you want. So you can replace this input with, #2, and you will sample it 2 nanoseconds or whatever your time scale is before the rising edge. You can replace this neg edge with #1 or #2, and you'll drive the signals 2 nanoseconds after the rising edge of the clock. So that's how you define the skew. Now, how do you define what is considered an input and an output? So input output is from the perspective of the test bench. Test bench is the one that is sampling D out. So it is an input, D out is an input into the test bench. And D in, this should say adder, and op are outputs of the test bench. They are things that the test bench drives into the DUTs. So I'll show you now how the test bench actually uses these values in the later example. But over here, you can see that we may want to take the interface, the clocking block declaration, and this data in value, and we want to drive it with 100. What this practically does, if you have a line like this in your test bench, is you will drive data in after the output skew with the value of 100. And similarly, if you want to wait for a clocking event, in this case, you can wait for .ckb. This refers to the clocking event defined as the event in the clocking block. So this will wait for the positive edge of the clock corresponding to this interface. And then in your test bench, if you want to fetch an output value from your DUT, like this D out value, which is an input value into the test bench, then you will sample it according to the input skew. So I will cover an example that walks through this in some more detail, helps you understand it a bit better, but it's a quick overview of these clocking blocks, what they're used for. Okay, now a big thing is object-oriented programming in System Verilog. So System Verilog has very typical object-oriented programming constructs that have been slapped onto the language on top of Verilog. So all the things you're used to from Java or C++ or Python, pretty much most of them are here. So you have classes, constructors, type generics, inheritance, virtual methods and classes. These are like abstract members of the class or abstract classes, and polymorphism or dynamic dispatch. So here's an example. You can declare a class. Again, class is a verification construct. It's not a synthesizable one. The class can contain any number of members. This is very similar to defining members in Java. And they can be of any data type you want. In this case, they're all bits and arrays. And then you can define a constructor. The magic keyword in System Verilog for that is new. And anything inside here is a constructor code. The constructor can have any arguments you want. And you can assign those arguments to the members of this class using the this keyword. This is also very similar to Java. And instantiating a class is very simple too. In initial block, you can just call new message, which this is the name of the class, and you specify the arguments to its constructor. And then you can access any of the class members using this dot syntax. So you can look at burst mode, you can look at any of these, and you can call additional functions that are defined in this class. And I'm just putting these in words because there's just too much stuff to talk about. You can extend a class. It's very simple to do. You just say class AOU message extends message, where this is an arg-defined class. Extended classes allow you to inherit all the functions from the parent class, inherits all of the class members of the parent class as well. You can call .super to access any of these superclass functions. For instance, in the subclass constructor, you may want to call the superclass constructor. Polymorphic dynamic dispatch works as usual. So you can have a bunch of child classes that have the type of the parent class. And then depending on the exact instance of the child class, you will call dynamically dispatch the function to that specific child class. You can declare classes and functions as virtual. All this means is you force a subclass to provide an implementation of a virtual function, or you prevent the instantiation of any abstract parent class. Class members can be declared static. This is just like Java, and this means that the class member is shared amongst all class instances. And these object-oriented constructs, why are they there in the first place, right? They're used to do two primary things. One is to model transactions, which we'll talk about later. And the second is to model hardware components. We can model them hierarchically by taking a CPU hardware component that we describe as a class, and inside that there is a cache, and inside that there is a memory and so forth. And you can use classes to define compositional hardware models. So you may have a CPU that you compose with an accelerator, and together these form an SoC. Okay, one of the neat features of System Verilog that again is shared in common with Java is classes can have parameters just like modules, but they don't merely have to be integers or strings or base types like this or structs and so forth. They can also be types. So this is similar to type generics in Java. And types are defined, type parameters are used to concretize this class prototype. And then we use the constructor to bind each class member to a concrete value. So here's an example. You have a FIFO, and the FIFO contains a fixed size array where the type of each element of that array is T, and T is a type parameter. So over here, you can put an int, you can put logic of any number of bits you want. You can put a struct. So it can be any user-defined data type. And this class will substitute this T for the concrete T over here. And then you can define functions that are also type generic. So push, for example, would push a value into the simulated FIFO. And that value pushes is of type T. And you may want to pull a value, and that will give you back a type T. A big issue, though, when System Verilog is you cannot define type bounds on T. So you cannot say that I want T to only be something that is synthesizable, or I want T to have an implementation of addition defined on it. This is something that you can do in Chisel, and Hassan gave a great example of how you might do it for the FIR filter, where you can say that I want T to be something that is synthesizable and something that has a ring type class defined on it. And that means you're making sure that T has something that has addition and multiplication defined on it, so that you can actually design an FIR filter with T. That is something you cannot do with System Verilog. Okay, so now we'll talk about a big topic here, which is the System Verilog assertions, or SVA for short. System Verilog assertions are the most complex component of System Verilog. There are entire books written on just this topic, and I think Bora will actually assign a few chapters of such a book to you to read. SVA is a temporal property specification language, and this allows you to formally specify some expected behavior of your RTL. But before we talk about SVA specifically, let's go back a bit and talk a bit more generally about assertions. So you probably are already familiar with asserts. the assert keyword. And the assert keyword gives you access to these so-called immediate assertions. And we're very familiar with putting assert, for instance, inside a test bench module, right? So you have a test bench module, you have an instance of your dot, and then you have an initial block. Inside your initial block, you set the inputs of the dot to something you want, and then you assert that the output equals what you expect. And so this is what you're familiar with from 151. There's a lot of tests written using this assert semantics. This is called an immediate assertion because it occurs during the execution of this sequential code in this initial block. And at this point in which you see it in that code execution is when you immediately check whether it is true or not. But this is insufficient to do a lot of more interesting things. For instance, how can I express properties that involve the microarchitecture of the RTL? So over here, you're checking for assertions on the outputs of your dot, but you want to perhaps have checks of things that are going on inside your dot that aren't exposed to your test bench. And you maybe want to express those properties in a very concise way. An example of such a property is some type of request acknowledge handshake, where after I send a request, you give me an acknowledgement within X number of cycles. How do I express a property like that in a concise way? I don't want to write code for it, a custom FSM to express such a property and to use with an immediate assertion. So the solution here is system Verilog assertions, which give you the ability to write concurrent assertions. These concurrent assertions, in contrast to the immediate ones, which are only triggered when you see them in a sequential block of code, they are constantly monitored by the RTL simulator. And these are oftentimes embedded inside the .rtl or an interface. So they're typically not part of the test bench code itself, but they are encoded as code inside the dot or around the dot inside its interface. So here's some very motivating examples of why you might want to use concurrent assertions. So the way you do a concurrent assertion is use the assert keyword, but instead of giving an exact value you want to check, you give a property. These properties form the core of system Verilog assertions. Properties are checked on a given event. So then after you specify property keyword, you specify the event. In this case, the positive edge of some clock in the CPU. And then you specify the property that you want to check. So here's an example of a property. If the lower two bits of a byte memory address are not equal to 00, and we perform a load word instruction, then this is an unaligned load. And perhaps you have a signal in your design called unaligned load, and you want to check that when these two things are true, that this signal is also true. So this is how you might want to write that assertion. This is the condition that you want to check. And if this condition is true, we use this implication to say, I want to imply that this must also be true. So now this property will be checked continuously as the RTL is being simulated. Similarly, you could define a property like this. If the opcode is equal to 0, then in the same cycle, I want to assert that some signal in my design called take exception is true because 0 is not a valid opcode. And I may also have a assertion like this. If memory stall is true, meaning that I haven't gotten the new instruction from my memory, then on the next cycle, I want to verify that my PC hasn't changed. And you can use a system function called stable to do that. And what this checks is that the PC from the cycle in which memstall was true and the PC in the cycle subsequent to that is the same. So to summarize this, properties are evaluated on a clock edge, and that is defined by these properties here, by these clock events here. We can use these two types of implication. This is the same cycle implication where you use this dash instead of equals, and you check that when the condition before the implication is true, at the very same time, the implied condition must be true. We also have next cycle implication, which over here says, if memstall is true, then on the next cycle, we check this property. What's very interesting about this specification language way of writing properties is that these properties can be formally verified. So a formal tool can actually take this property, it can look at your RTO and tell you that, yes, this property will always be true. Or it can tell you that, no, there's circumstances where this property isn't true, and here is the state of the design that would cause that to happen. So maybe we'll have a talk later in the semester about how to formally verify these, but this is the power of defining SVA properties, is they can be checked during dynamic simulation as well as being formally verified. I mentioned before there was a stable system function. System functions can be used in SVA expressions to simplify checking various historical properties. So if you're interested in what a signal did the cycle before, you maybe want to check that in the implication statement itself rather than before the implication. That will make the property easier to read. So stable is one of those system functions, just checks if some net X was unchanged from the previous clock cycle. There's rose and fell, which are useful for 1-bit signals. You just check if it rose on the cycle or the signal fell on the cycle. And pass to get the value of any signal X from any number. So you might want to use this to express a property like you have a pipeline register. And you may want to say that the RS1 in your memory stage is always equal to the RS1 in your execute stage, but on the previous cycle. So you can express very interesting historical temporal properties like this using these system functions. System Verilog properties, system Verilog assertion properties are made up of sequences and an implication. So we talked about have this implication, but everything that comes before the operator is a sequence. Sequences, of course, sequences of temporal sequences as atoms that exist independently of any other property. And then you can reuse these sequences to generate multiple different types of properties. So you can define a sequence called stall, and this sequence is equal to 1. So it's the simple as looking at a 1-bit signal. The sequence unchanged
We lost Vignesh.
Hello. Hey, can you hear
Yeah,
me now?
you dropped out. You stopped. Your connection was fading away, and we lost your screen. You're back.
Okay. Where was the last bit? This one? This slide here?
No.
This slide here?
Hang on. No, the one
Yeah,
after.
that's odd. This slide here?
Did you cover the one after that?
I was just going through this one over here.
Yeah, this one. Yeah, starting
Okay.
from that one.
Okay, so it looks like it didn't
the
lose
top
too
there.
much then. Okay. Yeah, sorry about that. So yeah, properties are made up of a sequence plus an implication. And many interfaces come with these sequence libraries that you can use to build more complex properties. Here's an example of how you take that property from the last slide and turn it into like a definition with sequence atoms. So here we have a sequence called stall that corresponds to when memstall is 1. You have a sequence called unchanged PC, and this refers to any time you advance the clock by 1 cycle and the PC remains stable. So this double hashtag syntax refers to advancement of a clock signal. Remember that clocks and events are not defined as part of sequences. So this hashtag 1 means that whatever clock you use in your property, this refers to 1 cycle of that clock. So now we have defined these 2 sequences. Now we can define a property. This property is stall holds the PC, of course. And then on a rising edge of a clock, if stall is true, then we imply that unchanged PC must also be true. But so properties combine these sequences with an implication. And finally, we assert that this property holds. And this is what actually causes the simulator to begin verifying that this condition always holds. There's all kinds of construction noise, I think, in my building. I'm sorry about that. Okay, so we have ways of combining sequences together. As I mentioned, sequences are the core of SVA, and they describe this temporal RTL behavior, and they can be combined with these temporal operators. So if you have a sequence A and a sequence B, then you can say that I want sequence A to occur, then I want one cycle to elapse, and then I want sequence B to occur. You can also say I want sequence A to occur, then n cycles to elapse, and then sequence B. Or you can constrain the number of cycles that need to be held in between A and B. And you can also specify that you want sequence A to happen, and then 2 or more cycles after you want sequence B to happen. You can also combine sequences using AND, intersect, and OR. And this basically means you waited for both sequences to succeed. This means you want both sequences to succeed and end at the same time. And this means you want either sequence to succeed, and the combined sequence ends whenever one of them succeeds. And as I mentioned before, you combine these sequences and the combinators that are used to join them together, finally with an implication, and that is what forms a property. This is really just scratching the surface. There's a lot more to SVA than sequences and properties. There's many more ways to combine them. There are local variables too, but we cannot get to that in time. The next thing we'll talk about is coverage, and the coverage API supported in System Verilog. So you're probably already familiar with software coverage tools. So you maybe want to track if a particular line of source code is hit by all the unit tests in your design, right? You have coverage. So coverage is used to measure the thoroughness of your test suite. How thoroughly did I exercise this software or this RTL given these unit tests? And you oftentimes want to answer the question, are all the interesting cases in this code exercised? So this is for software, but in RTL, we also have the notion of coverage. And it comes in 2 forms. There is structural coverage, which is very similar to software line coverage. We also have things like RTL toggle coverage, where we look at every register in the RTL design, and we ask whether every bit of that register has toggled from 0 to 1 and 1 to 0. And we also have condition coverage. So every time you have an if statement in your RTL, you may want to know whether I explored both branches of that if statement. So structural coverage is inferred by the structure of the RTL netlist. In contrast, we have functional coverage, which tries to answer the question, did a particular microarchitecture feature that was specified by a DV engineer get exercised? And so this is much more specific than looking at just some structure in the RTL. This refers to some microarchitectural flow that you want to check happened. So for instance, you want to cover maybe a cache eviction, or you may want to cover the circumstance of a misaligned memory access, or you want to cover an interrupt, that an interrupt occurred at some point, or you want to cover whether every opcode in your instruction space was executed by your CPU. So you want to check that all these different architectural level details actually happened. So how do you do that? Well, one way of doing it is property coverage. You can take any SVA property that we talked about before, and you can track it for coverage. Instead of using assert property, you use cover property. So for instance, we had this regac property where I have a request signal in my DUT. I want to see an acknowledged signal within 1 to 10 cycles after the request goes out. So maybe I want to cover how many times this has happened when I run all my unit tests through my RTL. And obviously you want this to happen at least once because you want to prove that this situation has been exercised by your test. These type of property covers are used in RTL to check that some multi-cycle microarchitectural behavior is exercised. So it's very easy to specify multi-cycle properties using SVA properties. And things like that would be, did this regex handshake occur? Or things more complex, like did a branch mispredict and then the subsequent predictor update happen? And did it happen correctly? This is something that you may want to assert as well as cover. There's also another API in System Verilog called the cover point API. Cover points allow you to track coverage of a single net. So this is not in reference to some temporal property, but this is just asking, I want to look at this net in my RTL, and I want to check whether this net has seen all of the potential values that it could take on. So an example would be a register that keeps track of an FSM's state. You may want to check, oh, did all the states actually get entered into during the test execution? You may want to track various control signals in your CPU or other data buses. And these cover points refer to a particular net, and then cover groups group together cover points. Again, each cover point refers to a net whose value is tracked at every cover group event. So cover groups are used to group together cover points that are sampled on one event. And that event oftentimes is a rising edge of a clock. These cover groups and cover points can be used in RTL as well as test bench code. And we'll talk about that a little bit later. Hopefully we have time. Here's an example of how you might want to use it. You have a module in your called CPU. You have some logic signals, RS1, RS2, and func3. These come from some instruction you parse. And you may want to cover that RS1 you have seen all the possible values of a RS1. Or you may want to cover that you've seen all the possible values of func3. So you define this cover group. And when you execute your tests in your RTL simulator, the simulator will track, okay, what are all the values that RS1 and func3 took on during the execution of all of these tests? And at the end, it will give you something like this. It'll tell you, oh, for the func3 values going from 8 actually doesn't exist. It should be from 0 to 7. It will tell you how many times func3 took on a particular value of either 10, 15, 10, 3. So it tells you how frequently each value was taken on. And then it tells you whether there's any coverage gaps. So here it might say, oh, func3 in the test you executed never took on the value of 1 or never took on the value of 5. And this usually means you have to improve your stimulus so that you're able to hit these additional points and test all your RTL thoroughly. Okay, final point on cover points. Sometimes we don't want to track each value a net can take on individually. Let's say I want to track an input of the ALU. That is a 32-bit value called A, and I assign a cover point for it. By default, every single value of A that it could take on, all the 2 to 32 values will get its own bin, and you will track how many times A was equal to each specific value. But we really don't want to do that. Sometimes we want to group some values together. And so here's an example of how you might do it. You define a cover group, you define a cover point. Again, this is referring to A. If we didn't specify anything in here naively, it would generate 2 to the 32 bins. But here we specify, I want to generate a bin to track how many times A was 0, how many times A was the max possible value, and then how many times A was somewhere in the middle. And this allows you to allocate 100 uniformly sized bins that fit in the range between 0 and max. So this is a much more reasonable way of tracking whether A approaches a uniform distribution. It is also useful for tracking whether there's special values that you want to be hit more frequently than others. So in an ALU, you're probably concerned about overflow. So you may want to hit max and min and 0 much more aggressively. Okay, transaction level modeling. This is now a verification concept. So our test benches are typically written at cycle level granularity. And this means that on every cycle, we figure out how we're going to drive something into the DUT. We need to figure out if something is coming out of the DUT, how are we going to verify that it's the correct thing? We need to use a golden modeling to do that. We may be interested in randomizing the timing details. So maybe we want to inject things into our FIFO that we're testing. at different intervals. We want to do it really quickly at one point and really slowly at another. And to generate that stimulus is also mixed into all of these other concerns, right? Driving, monitoring, the timing details, and so forth. Ideally, we want to separate each of these concerns in our test bench. And so the first step we can do that is called the transaction level modeling. We want to model a single interaction with the DUT as a transaction. A transaction is an abstract thing that could take multiple cycles in RTL, but represents a single interaction with the DUT. And this allows you to build a stimulus generator and golden model for the DUT at transaction level, meaning it operates by interactions caused by transactions. So here we have a memory request transaction, which specifies an address, write data, and op, and a memory response transaction, which specifies what it's getting back from the memory. And then we may want to define a golden model for this memory that has some internal RAM, and it has a way of processing a memory request transaction to give back a memory response transaction. Remember that everything here is just for simulation. This is a golden model of the memory. The actual memory itself may process a transaction over multiple cycles. So now how do we use these transactions in a larger test bench? Is we use these verification IPs. Verification IPs are what is used to translate between transactions and how the transactions are actually driven into a DUT at a cycle granularity. Verification IPs also allow you to translate cycle granularity interface activity back into transactions. And so here's how a test bench would be set up. You have your DUT, which is the memory I want to simulate and verify. You have your verification IP, which contains two different components, the driver, which does this first bit over here, and the monitor, which does the second bit. And they're both connected to the same memory interface. Then you generate your stimulus, which is given in the form of these memory request transactions. You feed them to the driver, and then the driver drives them into the memory interface. Each transaction can correspond to multiple cycles of bus activity. As that is occurring, the monitor is looking at that interface and it is decomposing those transactions into memory response transactions. It is taking the interface activity and it is generating memory response transactions from it. And then these memory request transactions, once you've exhausted all of them and pushed them into your DUT, and you've observed all of the memory response transactions coming out of the monitor, you take the same stimulus and you put it into the golden model we had in the previous slide, and you get the golden memory response transactions that you would expect from the DUT. And finally, you assert that these two things are equal. So this is a good way of creating a golden model-based test bench. And this is very typical for how a industry test bench may be architected. So a test bench has stimulus generation. It generates the golden DUT behavior. It simulates the actual DUT behavior. And then finally, it checks for correctness using this equality assertion. Okay, but are we running out of time? Almost. So how do we generate transaction level stimulus? This is the final point of System Verilog, which is constrained random generation. Any System Verilog class member can be prefixed with this rand keyword. And any class member that is marked as such is marked as randomizable. So you can define a class that has these rand fields. You can instantiate this class and call this .randomize function on it. And then System Verilog will automatically randomize all these fields, assuming a uniform distribution in the naive case. That's really neat. It's much better than having to type a bunch of $ randoms everywhere, right? But it gets even better because you can actually constrain the random fields of a class inside or outside the class, and you can add ad hoc constraints as well. These constraints are really powerful. Constraints you can basically write almost anything in these constraint expressions. Any synthesizable expression that tells you how you want each of the fields in your randomized class to be constrained with respect to each other. So here you might say that min has to be greater than 0, max less than 128, and you want to enforce that typical is in between min and max. You can also define additional constraints that should be defined outside of the class. So over here, you may want to specify a constraint outside the class that says min is greater than 5. And now when you call .randomize, you can even add additional constraints with the with keyword that are these ad hoc inline constraints. So now you maybe want to force, for the specific randomization instance, I want to force min to be 10. But I want to let the rest of these constraints dictate what tip and max could be. So this is really powerful because you can use constrained random to randomize variable length data structures. So let's say you have some packet that has a data array, variable length array consisting of 4-bit values. You can specify that I want the size of this array to be greater than 5 and less than 10. And what's really cool is you can actually put any function here. It doesn't need to be just size. You can actually specify that I want the sum to be something, that I want the product to be something else, whatever you want, really. And you can even do things like constrain each of the values of this data array that has a variable length size. You don't know what that size is, but you can still say that for every member, I want each of the values to be equal, to the index plus 1. And you maybe also want it to be inside a particular range, 0 to 8. So of course, this could fail in some cases if the size is too large, right? But this is just the beginning. There's many things I haven't discussed here. So constrained random is super powerful. You can specify various types of biasing and distribution for each of the random fields. You can specify soft constraints, disables. You can specify solving order. You can do implications, and there's ways to dynamically turn these constraints on and off. So it's a very powerful way of generating random stimulus. The final thing before the actual example, which I don't think we might get to, but there's a way built into System Verilog to communicate between threads. And the feature is called the mailboxes. And they're very similar to Golang channels if you've ever used Go before. They are bounded queues that allow one thread to send data to another. So very simple to use it. You can construct a mailbox of a particular type, specify how many elements the mailbox can have. And here we have 2 threads defined by 2 initial blocks. And one block can put stuff in the mailbox with .put, and the other block can get things in the mailbox with .get. And you can call .num to see how many elements are in the mailbox. This is just a very simple way of communicating between 2 threads. And this thread-safe communication is built into the language. So I think I'll stop here. There is an example of a test bench that uses all of these things that we just talked about. Actually, Bora, you can let me know if you want me to go through the rest of these 3 slides here, or I can skip to the conclusion.
Yeah, I think we're out of time. We can probably we can cover them perhaps next time. It would take 10-15 minutes. It's not gonna. This is not an instant one.
It's up to you.
Yeah, we'll discuss it. Yeah.
Okay.
Thank
So
you.
in conclusion, System Verilog is great. So hopefully you learned something in this lecture, and feel free to send any questions you have my way.
Okay, thank you, Vignesh. And thanks, everyone. All right. See you next week.